So in this video, you will learn the basic control system design and flight simulation for a rocket taking off and landing. This will be a 3DOF simulation because the 6DOF will take too long to teach. So obviously I'll start off with something much faster. You will learn rocket propulsion basics, the review of that, the gravity turn, how it works and why it's so important. Lastly, you will learn also the landing control system design to change the pitch angle, and then building a full flight simulation from scratch. So we have our engine model there. This is taken from the SpaceX Falcon 1 manual. It's a very old manual, it's outdated now, but I needed to get the values from there. So we have the force from the engine at sea level and vacuum. You have the specific impulse. From that you can get the mass flow rate because impulse equals force over m dot times g. So you can solve for the mass flow rate there. We have about 169 seconds burn time. You can also get the amount of fuel that you have, so the amount of propellant inside the rocket. That's important because you need to know what the mass is in real time, because the mass will change, right? It's a variable mass system. So I did a hand calculation there, so you can approximate the mass flow rate to give a similar burn time. It'll not be the same, but we can assume this for now. To make things simple, we can assume a constant force from the engine and a specific mass flow rate for a specified burn time. This is obviously not real because in real life you have the pressure changing outside, and based on the rocket propulsion equation you will have a variable force, but for this simulation we can just assume it's constant. We have the vehicle model, a generic launch vehicle. We have a specified dry mass, fuel mass, payload mass, length, diameter, and the center of gravity location, so it's 7 meters from the base. So these are just some numbers I put, and you can use them for simulation purposes. Now we have the gravity turn equation. So this is basically V is velocity, T is your force, D is drag, M is mass, G is your g-force, and gamma is the pitch angle, or more specifically the flight path angle. So when we lift off and we ascend, we will assume that the pitch angle is equal to the flight path angle because the force points along the rocket body. But when we land, it'll be a bit different because you will flip the rocket, right? You will initiate the boostback burn and do the flips. So the pitch angle will be separated and it'll be defined by the force of the cold gas propulsion system multiplied by the value of d2, so that's the moment, and divided by the moment of inertia. So you will flip the vehicle and then land it. So the pitch angle will obviously change. RE equals radius of the earth and h equals height. So you can see what I mean here. We have liftoff. So now in phase 1, the pitch angle, if you see, it's equal to the flight path angle, so it's going along that direction. But in phase 2, the pitch angle is different, right? The flight path angle is going all the way down, but the pitch angle is pitching up because we want the rocket to land vertically, so it has to be like this. And in landing, the pitch angle should be 90 degrees up, but the flight path angle should be negative 90 down because it should be descending. So for our simulation, you will have these results or something similar to that. So takeoff is about 100 seconds, landing is about 200 seconds it takes to from like the boost back burn to landing. You have almost the speed of sound reached for your max speed. It goes to about 32 kilometers, which is not too bad. The touchdown speed is about 150 meters per second. Now that is a high value, but keep in mind that you have to slow it down from this value, right? So I mean, I tried my best to slow it down as much as possible. If I slow it down any more, it was not too, I mean, it took a long time to land, but obviously you can't land too fast, right? Because then it'll crash on impact. So it has to be a decent value. The liftoff force is the maximum force from the engine. The initial orientation is pitched up, so it'll be 90 degrees for flight path angle and pitch angle. The landing pad distance from the launch site equals about 84 kilometers. So it'll go about 84 kilometers downrange from your launch site. I chose Cape Canaveral to be the launch site at about 28.6 north and 80.6 west. So here we have the free body diagram to see what I mean in the visual form, so it's better. So we have H and X. We have your force, your drag, your flight path angle, so it's going like this. Your weight mg, speed v. Drag equals, from fluid mechanics 101, it's half rho v squared times your drag coefficient CD times your area A. So now we assume that the pitch angle equals the flight path angle during ascent, okay? Because obviously we have to get an expression for that. So initially we can assume this is true, but when we initiate the boost back burn, it'll change. The Earth radius, you should all know what that is. It's a constant value. So now when we land, you will flip the rocket and you will land like this, right? So it'll be, the pitch angle will change. It'll be some different value. And the flight path angle will still be negative because it's going down. So the flight path angle tells you how much is going down. And mg will always point down. Now since it is going this way, the drag will be opposing the speed vector because it always opposes the way you move. But now the engine force, if you look at this diagram, it is flipped, right? So now what's going to happen? The force from the engine will point in the same direction in the drag and it'll oppose the speed. So what's happening now is that the engine force is actually slowing down the vehicle, and that is what the boost back burn is, because you activate the force in the opposite direction to slow the vehicle down. Before we had force and speed in the same direction, so it is speeding up, but now since we do a flip, it's slowing down. And if you look at this diagram from SpaceX here, you can clearly see that there. So you can see that the flight path angle becomes more and more negative, but they do also flip the first stage for landing, and then they initiate the boost back burn, and that'll slow the vehicle down. So when we have impact, you must ensure that the speed is very low and you have the pitch angle as close to 90 degrees as possible. This was always the case. Even if you look at the old Apollo missions in this diagram here, you can see that the flight path angle is almost vertical, and that's what we need because it should be a vertical descent. You don't want the rocket to land like this, right? You want it to land straight down. Yeah, now we can begin the model in Simulink and Matlab. Open a new Matlab file and begin typing all the parameters. So you have the engine model there. You also have the vehicle model. The zero fuel weight, ZFW, is equal to the payload plus the dry mass. You also have all the initial conditions, which you can type in there yourself. The velocity should be a bit non-zero, because then you will avoid division by 0. And then you will have a pulse input of the gravity turn initiation after some time. So save that as parameters.m, as you can see there. Run it and then load it in a workspace. Open the new Simulink model and drag the functions in there. We have for thrust, pitch, and drag. So we can just define all the variables that we need for now and then edit the functions after. So we can do that there. Save this as flight_sim. Do the same thing for the pitch command. So this will be the pitch angle that we command after some time to initiate the landing. And for drag, we can do the same thing. It's based on the height h and v, speed v. So that's it. Let's drag in all the blocks that we need. So constant, addition, product, multiplication, like all that stuff. Display, scope, a clock for timing, because we will need that as well. Product for multiplication. Divide. Scope for and from and go to blocks. These we will use a lot to route a signal. And we can also drag in a sum block and a gain block for multiplication, along with for sine and cosine, the trig functions there. So drag all those. So now let's begin the definitions. That's your mass flow rate, m dot. We have thrust minus drag, as you can see there. We have to solve for the mass of the vehicle in real time, so you can do that very simply here. So drag in the mass of the fuel burned. ZFW is the zero fuel weight, so we subtract those very easily. So this is thrust minus drag divided by mass. So this will be the G sine term, which we will define after, so we can just set it up for now. So it's G sine of gamma. Let's do the integrator dv over dt for velocity, so that's v0 initial conditions. So V sine of gamma will go there. Then we have dH over dt for the height. Now we can get drag from height and speed, so we can just connect those blocks very clearly there. So connect V and then connect H. So that's your height and your speed. From there you can get your drag. So we can now do compare to 0, and when the height becomes 0, the simulation will stop. So just drag in a stop block and connect that to your height, as I'm doing here. We can also look at the height as a display, so we can do that, and we can next drag in a scope block to see the height in graph, just like so. Or just put the drag in there, so T minus D. Alright, now we can move on. We'll do the pitch after, so we can just drag in some go-to blocks. So we have the thrust as T over there. Drag a go-to block for your height, H, and drag in another one for speed, V. Okay, so we have that there, and we can drag in a scope block for speed also, along with the display if you wish. So just connect that to speed for velocity. Meters per second, right? So, alright, now we can drag in the from block for H, T, and gamma. But gamma we don't have yet, so we have to define it after. So first we can do some more stuff. We can do the Earth radius equation, RE over RE plus H, that term. It should be RE, okay? So just change that in the Matlab command. So that's RE plus H, we have that there. Then we have RE over RE plus H, so we can just divide it like this. Just drag it and adjust it. So now we're doing dx over dt. Because that's the downrange distance equation as we need. We can drag in a display block to see what that looks like. And also drag in a to block from the signal to make sure that you can drag it after anywhere you want to. So now we have H, so we have all the things that we need. So that's your gravity G. So now we're doing the next equation here. So we just have to drag in the from blocks now. So this is for d gamma over dt. So we have to first define some stuff, as you can see. Or let's drag in the to block for RE plus H. So that's RH. I called it that variable. So that's G over V. So that's gravity divided by velocity. And this will be here V over RE plus H. So we can just simply divide them out. So that's your d gamma over dt equation, but it'll be multiplied by cosine of gamma. So we have to get the cosine first, which we will do in a minute. But just drag that across to make sure that it looks neat. So that's your gamma over dt integrator term. Gam 0 initial condition, that's 90 degrees pitched up. So we have that. V cosine of gamma as there. So do a cosine there. So now we're connecting the sine gamma term up there, and then that's cosine of gamma. So that'll go into x, right? Because it goes into that from the x equation. Then we have gamma, we can do it from and to block once again. We can also drag in a scope and display block to look at the flight path angle, that's gamma. It just makes things easier in the simulation to check for results very easily, instead of, clicking the variable and looking at the output that way. So now we have to drag in a gamma from block and do v sine of gamma for the top equation. So that'll be a sine. And gamma from, so that's done. So that's cosine of gamma there. And we have to lastly do the gamma pitch input. So that'll be a step command, because after a few seconds we have to initiate the gravity turn. So just do this. Drag in 2 step blocks and then add them up. So that'll be the turn time, gamma initial, and final value of 0. And the bottom block will be just 1 second after, and put in a negative there. And add those up and then connect it there. So we have your gamma input now. So that'll basically initiate the gravity turn. Now we can just drag in more stuff to complete the pitch angle command. That's the PID controller. We'll be using a derivative controller, PD, because we have a second order system which is marginally stable. So we have to... A PD controller works best because it'll make the closed loop system not overshoot. And you will have very good performance. So it actually is just a D controller, so it'll just be the derivative term is non-zero. So put it to 100 over 5. So then you have to multiply it by your d2 over jy term, that's 5 over 200. Then we have d dot and dot because of the equation. And we can get the pitch angle from there and then compare it with the set point. So we have the negative feedback as obviously required in a control system. We can also use 2 blocks for the pitch angle there. Now we can define the functions, right? So for the thrust command, define 2 persistent variables. It means that they retain their values every time they're called. So it's saved in memory, right? So it's very important to define it that way. Define the fuel mass in kilograms. And if it's less than 65%, you activate full power. So we are only burning 65% of the fuel at liftoff. And after some time, that's your entry burn and boost back burn. So we have a negative value because I explained in the equation before. And then just output everything. So that's not too difficult. You're just setting the value and then outputting all that along with the mass burned, so we can get the mass in real time. So for drag, it's very easy. You have to use the standard atmosphere model. So I just did that there. Define the drag coefficient, the diameter, and the area. Now this I just copied from the ISA model, which I'll put there on the left, so you can get a reference as well. So you solve for temperature and pressure, that's T and P, and then you get your density after that, which is based on obviously pressure and temperature, right? So rho is density, and then you get your drag. So that's half rho v squared times area times the drag coefficient, and output that. Change the initial condition for the pitch angle at pi over 2 and make that 0 for dot. So now that's your pitch command there. So that's your flag variable f. So when we initiate the boost back burn, it'll be set to 1, so we know what happens. So if your force becomes negative, it'll be gam plus pi because we have to do an inverted flip. And if height's less than 1000 meters, we have to make sure that it is perpendicular to the ground, so make it pi over 2. And if it's nothing like that, then you make it gamma. So that's your pitch angle command. And basically before you initiate the boost back burn, the pitch angle is equal to gamma, so that's why I did it that way. Lastly, check your solver settings, stop time and ODE45, the dormant prints method. Run this and see what you get. So the height's too high, so we need to add more time. The pitch angle is obviously not 90 degrees yet, so add 50 seconds more. So now we have good performance. We have the speed at 149 meters per second. The height goes to 0. So it takes off and then lands. So it's quite good. Your speed goes to almost 0, but then it speeds up because obviously the boostback burn and the entry burn is disabled. The pitch angle goes to 90 degrees as you can see there on the rightmost side. So that's about 90 degrees. So that's good. And the flight path angle is negative, so that's awesome, right? So that is what we need. You can see the flight path angle change with time there. So it goes from plus 90 to negative 90. It goes about 84 kilometers downrange from the launch pad. So that's not too bad, right? I mean, so the landing pad must be about 85 kilometers from the launch pad. You can connect it to FlightGear if you want to. I have many videos on that, so I'm not going to explain the whole process, but you have to use all these blocks here. That's your launch site location. We can define the roll angle to be pi or 0, doesn't matter. Pitch angle and yaw angle, and then we can use the aerospace toolbox to connect it to FlightGear. But if you don't have that, you can use this here. So Matlab has the 6 DOF animation, so all you do is you drag in X, Y, and Z. Z is height, Y is 0, X is your downrange distance. You drag that in here. And also roll, pitch, and yaw. Roll and yaw is 0, pitch angle we need. And then drag in the 6 DOF animation block. You can see what it looks like here. It takes off now, so the height's going up. If you look at the H value there. So it's going up pretty fast, right? Then it drops. So it goes to about 32 kilometers and then goes down. So it does go a long way, right? I mean, it goes to about 85 kilometers if you look at the X value from the top. So height's descending, it'll stop soon at 0. So it's a vertical descent, so that's very good and that's something we need. And if you look at the simulation in FlightGear, so that's Cape Canaveral launch site. I mean, it's not the exact coordinates, so it's sea there, but it'll actually be land if you look at the real place on Google Earth. So we have the launch there. So yeah, initially it'll go up straight, and after about half a minute we will initiate the gravity turn. That is why I put the step command there, as you saw, for gamma in and T time, the turn time. So it's still going up, I think vertically, and soon you will start the gravity turn, so you'll see it here. So now it's pitching, it's doing the gravity turn. You can see the engines there. I just downloaded a model and then imported that. I also have videos on how to import CAD models to FlightGear, which I will link. It might be useful to you. You can change the view position there and you can see what it looks like in launch. So yeah, that's it. Here you can see what would happen if you don't have a power descent versus if you do have one. So on the left, to obtain this graph, between 125 and 200 seconds in your force function, just make it 0 and you will have this result here. You can see how the landing speed is way too fast and the pitch angle is not good because it's going like that. So this would be a disaster. If this was in real life, the rocket would blow up the second it hits the ground, and that is something you don't want because obviously it's not good. Because the speed is way too fast, right? It's moving at Mach 1. It's basically just falling down as a projectile. And that is why it's so important to initiate the power descent, because it has to descend very slowly and softly. And you have a big difference, so it's slowing down all the way. So between 125 and 200 seconds, you will have the force. It does slow it down quite a bit, but then it speeds up a little bit because I turned the force off. So I mean, but that's okay because it's not too bad still. The most important though is the flight path angle. It is 90 degrees and that's what we need for a vertical descent. So yeah, you can see how important it is to initiate the boost back burn and the entry burn.